Hi everybody, Mr. Gerhard here, and we're going to talk about 6.3, which is function operations and composition. This is with power functions, which is a little bit different than polynomials. All polynomials are power functions, but not all power functions are polynomials. Power function has a form y equals ax to the b, where a is a real number and b is a rational number. And then the composition of a function is when we plug one function into another. And we'll talk about that one a little bit later. But the first thing we're going to do is we're going to start off by working with addition and subtraction of functions. And so the first one that we have is we have f of x equals negative 3x to the 1/3, and g of x equals negative x to the 1/3. And we have to find f of x plus g of x, f of x minus g of x, and then talk about domains. So for the first one, we have f of x plus g of x. What I'm going to do is I'm going to substitute negative 3x to the 1/3 in for f of x, and I'm going to substitute in negative x to the 1/3 for g of x. Now I'm going to put that in parentheses because of the positive negative there. Now if I have negative 3x to the 1/3 plus negative 1x to the 1/3, I'm actually going to have negative 4x to the 1/3. I just simply add the coefficients of like terms, and that's what I get, negative 4x to the 1/3. For part B, it's asking us to do the same thing except now with subtraction. So we're going to say f of x minus g of x. And so f of x, again, is negative 3x to the 1/3. So I write that down, substituting for f of x, minus negative x to the 1/3. Because I have a minus minus, I'm going to change those signs because subtraction is like adding the opposite. So I don't get confused, I change those signs. Now I have negative 3x to the 1/3 plus x to the 1/3, and that's just going to give me negative 2x to the 1/3. And that's my final answer. Now when we talk about domains, remember our domain rules. Domain rule number 1 is you can't divide by 0. And domain rule number 2 is you can't even root a negative. All right. So here we're doing to the 1/3 power. X is being raised to the 1/3 power. And so our domain for f of x is all real numbers because we're not dividing and we're not even rooting. Same thing here for g of x. X to the 1/3 power, remember that x to the 1/3 power means the cube root of x, cube being an odd root, and so we can even root or we can odd root any type of number. And so the domains for both f plus g and f minus g is all real numbers, which we can put like that, or we could say from negative infinity to infinity, which is interval notation. And so the domains is not a pretty big deal here. It will become a bigger deal as we go on. Now when we start to multiply and divide functions, this is going to cause a little bit of problems with the domains. Here again we can see that f of x equals 2x squared, g of x equals x to the 1/2. And so what I'm going to do is I'm going to put in for f of x 2x squared. For g of x I'm going to put x to the 1/2 power. And we just simplify by combining terms and multiplying and using our exponent properties. The 2 is by itself, so that's going to hang out. And the x squared times x to the 1/2, when we have like bases, we add the exponents. And so 2 plus 1/2 is 2.5, which we want to keep as an improper fraction, which means 2x to the 5/2. That's the product, or the answer to the multiplication problem. If we change over here and go to the division problem where we have f of x divided by g of x, I'm going to say 2x squared divided by x to the 1/2 power. And again, the 2 is just kind of hanging out. And then when we have division, what we do is we subtract those exponents. 2 minus 1/2 is 1.5, which as an improper fraction is 3/2. So I get 2x to the 3/2 power, and that's as simplified as I can go. Now the domains of f times g and f divided by g, we have to look at both what f of x is and what the domain would be. if f of x is equal to 2x squared, we don't have any dividing going on, we don't have any even rooting going on, and so the domain of that is all real numbers. We can put anything in and we'll get a number out. For g of x, we have x to the 1/2 power, which if you remember, when we raise something to the 1/2 power, that's a square root. So x to the 1/2 is equal to the square root of x. What does that mean? Well, it means that x has to be greater than or equal to 0. And that's because we cannot even root a negative number. And so our domain here is x has got to be greater than or equal to 0. So when I do this part right here, and I go back and I look at f of x times g of x, which is what we did in the blue pen here, I have to look and say, okay, well, I can plug any real number in to 2x squared, but I can only use non-negative numbers, which would be x is greater than or equal to 0 for this. If I look at the final answer, same idea. I have an even root because of this 2, and so my domain for f of x times g of x is greater than or equal to 0, because that will allow me to do the even rooting, and it will allow me to do the multiplication. When I come over here and I look at f of x divided by g of x, again, the domain for the top could be all real numbers. Domain for the bottom could be x has got to be greater than or equal to 0. The only problem with that is if I put in 0, square root of 0 is 0, and then I have 0 in the denominator. And we can't have 0 in the denominator. And so for this problem, I need to say the domain is all x's greater than 0. Because if I put in a negative number, I won't be able to square root it. If I put in 0, it will give me 0 in the denominator, and that will be not allowed. It's a domain rule number 1. So that's bad news. So that would be our domain for f of x divided by g of x. Now, composition of functions is when we plug one function into another. And so when I see something like this, we're going to close that. All right. When I see something like this, what we're doing is we're plugging something into f, the input of f, and that becomes the output after we do f of x. And then what happens is I take that output and I plug it into g. And so this function here is g of x. And the input, or the output I should say, of f becomes the input of g. They're the same thing. And so that's kind of how this composition of functions works. It's putting one thing into another. So the composition of a function g with a function f is g of f of x. We're plugging one function into the other. The domain is a set of all x values such that x is in the function in the domain of g, or x is in the domain of f. I'm sorry. Let me erase that. X is in the domain of f, and f of x is in the domain of g. So we'll talk about that as we do an example. So here we have f of x equals 2x cubed, g of x equals x to the negative 1. And when I see f of g of x, what I'm going to do is I'm going to take this g of x and I'm going to substitute what I have in there, x to the negative 1. Now, x to the negative 1 will go where there's an x in f, because I'm replacing x with x to the negative 1. So instead of 2x to the third, I have 2x to the negative 1 to the third. And you can see right here where the x to the negative 1, that's not showing up very good, x to the negative 1 is replacing the x in our original. Now the last thing that we have to do is just simplify this. Power to a power means we multiply, and I get 2x to the negative third power, or 2 over x cubed, so we don't have any negative exponents. For g of f of x, I'm going to go ahead and do the same thing. I'm going to say g of f of x. Now one of the things that we can do, and maybe this will make it a little bit easier, is I'll replace this x with f of x, because this is what's going into g. And so I could say f of x to the negative 1. And when I see f of x is 2x to the third, I can say 2x to the third to the negative 1. And now I distribute this negative 1 there and there. And that's going to give me 2 to the negative 1 and x to the negative 3. Because they're both negative exponents, they would go on the bottom. And I would say 1 over 2x cubed is my solution. Now when we talk about domains, the domain for f of x, let me go up here, domain for f of x is 2x cubed. That's going to be all real numbers because I'm not dividing, I'm not even rooting. Same thing down here, g of x has x to the negative 1. And so that's really like 1 over x. And so my domain is all x's except for 0, because that would be dividing by 0. And when I go and plug stuff in, here my domain is all reals except for 0, because I can't have 0 initially. And then I can say that any answer that I get out would be anything but 0 as well. So we'd say all x's not equal to 0. Here, for f of x, the domain here is all real numbers, but the problem is when I take that, my answer can't be 0 because then it's going to be on the bottom. And so I can't plug anything in down here that would give me 0 either, so that would mean that x can't be 0 here as well. And there's our domains for the two. That's a little tricky, and we're going to work on that as we go through. One last thing, here's f of x and g of x. And we're going to do where we can evaluate for a specific value. For example, f of g of 1. Now, if I'm going to do this, I'm going to just do f of g of 1, and I'm going to say f of, and now g of 1 means it's going to be 1 squared minus 1. Well, 1 squared is 1. 1 minus 1 is 0. And now I'm trying to do f of 0. Well, f of 0 is now 2 times 0 plus 3. 2 times 0 is 0, plus 3 is 3. And so that's my f of g of 1. If I try the other one, g of f of 2, what's going to happen now is I'm going to plug 2 into f. So it's going to be g of 2 times 2 plus 3. That's going to be g of, let's see, 4 plus 3, which is 7. And then I take the 7 and I plug it back in. I say 7 squared minus 1, because x squared minus 1 is g of x. That's 49 minus 1, so that's 48. And that's how we evaluate composition of functions with actual numbers. So I know we went over a lot. Take a look or another look at the actual video. Try some of the problems, and we'll talk about it more tomorrow.